The Net Zero Energy Ready Challenge is a Clean BC incentive program and juried competition for large buildings launched in 2018. It provides financial support for developments targeting net zero energy ready levels of performance and aims to celebrate, promote, and learn from BC's most innovative and energy efficient projects. Integral Group and Vancouver's Zero Emissions Building Exchange have commissioned a series of 6 technical playbooks and accompanying videos to help our development, design, and construction communities make net zero energy ready buildings a reality before they are required throughout the province in 2032.
Hi, my name is Marie Veneri, and I'm a principal at the AME Group. I've been designing mechanical systems for buildings for over 15 years. I'm here today to talk about electrification of heating and domestic hot water systems in buildings. New building construction projects are everywhere in British Columbia. With so much construction happening, what does the future look like for building systems? Heating and domestic hot water use up to 60% of the building's energy and are the systems that have the biggest impact on the building's ongoing greenhouse gas emissions. In 2015, 17% of BC's GHG emissions came from buildings. This is why government policies are moving towards having greenhouse gas intensity, or GHGI targets. As we educate ourselves as designers, owners, and developers, we better understand the methods and technologies available in establishing the framework for a low-carbon future in buildings. In this presentation, we will review electrification of heating and domestic hot water solutions. The different mechanical systems explained can be applied to a multitude of building types, as well as both new construction and retrofits. Most building greenhouse gas emissions are the result of burning fossil fuels for heating energy and domestic hot water. We want to focus on moving towards electricity. Luckily, in British Columbia, we have some of the cleanest electricity in the world. BC Hydro maintains 93% of its energy to be generated from clean or renewable resources as part of BC's Clean Energy Act. The majority of BC Hydro's electricity is generated from hydroelectric dams. There are also some smaller plants made up of wind, solar, and biomass facilities. BC Hydro's goal is to increase their generation, transmission, and distribution while keeping electricity affordable. Energy storage technologies are improving each year, which helps ensure electricity is kept affordable for the future. With BC's abundant supply of clean electricity, fuel switching from natural gas to electricity becomes the most reliable strategy for reducing carbon in buildings. The main reason for continuing to use natural gas in buildings is that it is still more affordable than electricity. In Vancouver, for example, the cost of natural gas is about 3 cents per kilowatt hour, and electricity is approximately 11 cents per kilowatt hour. There are approaches and technologies available in reducing operational energy costs. The province of BC has set the bar and legislated GHG targets to be 40% below 2007 levels by 2030, 60% by 2040, and 80% by 2050. Many municipalities, agencies, developers, and institutions have recognized these targets and have set their own goals to align with the province. Most of these GHG policies have been written into bylaws and owner technical guidelines. For example, when rezoning in many municipalities, in addition to meeting energy use targets, there are now GHGI targets. Rebates are widely available in BC for both new construction and retrofits that demonstrate low greenhouse gas emission solutions. These capital incentive programs have recently changed their baseline models from kilowatt hours of energy to GHGI targets as well. If you are an owner or developer, reach out to your consultant team or utility provider to see if you can take advantage of any of these programs. The building heating systems are sized based on the performance of the building envelope. The better the insulation or the air tightness, the less amount of heat is required, which is why the first step in reducing our GHG emissions would be to first look at improving our envelope. Similarly, for domestic hot water heating systems, by using low-flow fixtures, we reduce the amount of energy required as we have less water to heat. There are a number of different types of heating systems for buildings. There really is no one best system. In fact, the best system for the project will depend on a variety of factors: the building type, size, energy targets, ownership, and cost. capital and ongoing. Let's review some electric heating system options. This first one is, of course, the traditional electric baseboard heater. This is simply a heating element that will turn on or off as needed to maintain the space temperature. These are generally installed with 1 unit per room. This ensures that the room that needs the heating will get the heating. This is the simple, low capital cost solution and used in many buildings. It only needs an electric connection and a thermostat as infrastructure. It is a good option for buildings that are only providing heating. The measure of a system efficiency is based on its coefficient of performance, or COP. This is the amount of electric energy that is required to produce heating energy. For an electric baseboard heater, the COP is 1. 1 kilowatt of electric energy in is equal to 1 kilowatt of heating energy out. Although this sounds efficient, there are technologies available with higher COPs. The key to efficient electric heating systems are heat pumps. This technology can have COPs upwards of 3. Meaning these can have 1 kilowatt of electric energy in and 3 kilowatts of heating energy out. How does this work? An air conditioner uses a refrigerant loop, which includes a compressor to move heat energy from inside the building to outside. A heat pump uses the same technology, just in reverse. It moves the heat energy from outside through a refrigeration cycle, where a compressor powered by electricity adds energy to the refrigeration loop. The system then moves that energy inside the building as heat. With a unit of electricity in Vancouver being 3 times the cost of natural gas, using heat pump technology with efficiencies at 3 times the traditional electric element, it makes these technologies more cost-effective in keeping energy costs down. Heat pump systems can either be air-cooled, where the heat energy is transferred directly from the atmosphere, or it can be water-cooled, where it transfers it from a ground loop, a loop in the ocean or lake. Regardless of how cold the source may appear, there is still energy to be moved. One of the benefits in using heat pump technology in our buildings is that we can use the same system for both heating and cooling. There are different types of units that use this technology, and they vary in scale from small one-room units to larger central systems. Package terminal air conditioning units, or PTACs, are wall-mounted units installed on an exterior wall, typically below a window. These are small, packaged independent units where the entire system is located within that unit. These can be supplied with heat pump technology. It has a grill on the exterior wall, which is where the energy is moved from the atmosphere into the refrigeration loop and then into the space. The advantage of these units is that they don't need any piping or central plant infrastructure to provide the heating in the space. And with the heat pump technology, they have a high COP. Although they are efficient on their own, there is no benefit in recovering heat from a whole building perspective. A variable refrigerant flow, or VRF, does provide for a whole building heat recovery system. There are 2 types of VRF, water-cooled and air-cooled. Both are similar in how they operate. However, the air-cooled option is the simplest to provide as a fully electric-based system. The system includes an air-cooled condenser located outside, with refrigerant piping that runs down to the building to all the fan coils in the suites. There's one small additional unit that sits in between the two, called a heat recovery box. This is typically located centrally on each floor, which consists of control valves and sensors. Essentially, it's the brain of the heat recovery system. How it works is that when one fan coil is in cooling, the heat being moved from that suite is first analyzed by the box. If that system determines that another fan coil in another suite on that same floor needs the heat, it will move that heat to that unit. If there is no need for heat, it will move it up to the condensing unit, where it is rejected to the atmosphere. When the entire building is in need of heat, however, like in peak winter, the air-cooled condensers will operate in heat pump mode and move the heat energy from the atmosphere into the building. This is a simple package system, all supplied by the same manufacturer. It has integrated controls and has a high COP. There are limitations such as building height, climate, and routing of refrigeration piping, which should be discussed with the design team. An air source heat pump, typically located outside on a roof, will move heat energy from the atmosphere into the heating water piping system, which is distributed through the building, where it ties into terminal units, such as fan coils. There are different types of air source heat pump technologies available. in which some can operate with a heat recovery mode. When in this mode, the control system will monitor the amount of cooling in the building and then see if any spaces within the building are looking for heat first, which it will then move into the heating water system before it rejects it to the atmosphere. If the entire building is in need of heat, however, it will operate in full heat pump mode and move the heat energy from the atmosphere into the building. This system has a high COP and is a slightly more complex system in that all the components can be from different manufacturers, which requires an independent control system design. This system does allow flexibility with different types of terminal units, like fan coils, hydronic baseboard heaters, or radiant panels. Domestic hot water typically uses fossil fuels as a heating source. Similar to a building heating system, we have different types of technologies that can be used in moving to an all-electric based system. The first technology is a simple electric hot water tank. This is a heating element inside a tank that will power on to maintain a tank temperature. This can either be installed as a central system and piped throughout the building to all the suites, or it can be decentralized, where we have smaller electric tanks inside each suite. This is a simple, traditional, low capital cost solution. For more efficient systems, we need to look at using heat pump technologies again. This is a growing application in BC, mainly because of the many new GHGI targets that are being implemented, as discussed earlier. There are a few different methods for domestic hot water heat pump applications. These all have COPs upwards of 3 or more, making these more efficient than the typical electric domestic hot water tanks. In a decentralized system, we can have all-in-one domestic hot water storage tank and air-cooled heat pump packaged together. These units are generally smaller tanks, similar size to the one you would have in a single-family home. The heat pump itself sits on top of the tank and will move the energy from the room into the water in the tank. This unit is best installed in a space that will generally remain warm, like a furnace room or utility closet. These include their own package controls and require no additional infrastructure, similar to a traditional electric hot water tank. We can also use the same type of air source heat pumps as we would for the building heating system for domestic hot water heating. A central unit outside, piped with hydronic water into a domestic hot water storage tank where the water is heated and then piped to the suites in the building. This is a more complex system from a controllability perspective, however allows flexibility in using different manufacturer for the different components. It also requires more infrastructure and is found to be most cost-effective in larger buildings. There are a few new emerging technologies available, one of which is using CO2 as a refrigerant instead of the typical hydrofluorocarbon refrigerants. CO2 is a naturally occurring substance, but it is much more efficient. Heat pumps using CO2 can have COPs of up to 5. These are generally available in smaller sized tanks, like for single-family dwellings. For larger scale projects, we can use the heat in our sewers. This system will pump sewage through the heat pump, where the refrigeration loop then moves the heat energy into a heating water system, which then flows into a tank filled with cold domestic water. The heated water will then flow to the fixtures throughout the building. Don't worry, both sides are completely separated by the heat pump. Thank you so much for watching. For more information about electrification of our heating systems, please see the full playbook on the ZEBx website. This presentation is part of the ZEBx Net Zero Energy Ready Playbook series.